So here's our kidney dissection, and here you can see a whole kidney. You can see the hilar fat pad right there. It's super, super dense. And then what you can also see is the 3 different layers of the kidney. The outer layer, that cortex part, is pretty solid, and then the medulla is the middle layer, and then you can see here the pyramids in the medulla. So it's kind of nice because you have the blue dye showing you all the striations of the medulla, but here's pyramid, 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 pyramid. And this one is also kind of cut in a way where you can see the tip of the pyramid right here. And the pyramid is made up of a whole bunch of collecting ducts that all kind of funnel into the tip like a shower head. And so at the shower head, that's where all of the drops of urine come in. They enter the minor calyx and then enter the major calyx like a watershed, and then eventually they make it down all the way into the pelvis right here, the renal pelvis. And so after that, the urine goes from the renal pelvis out. I'm going to stick the probe in here and see if it works. Aha, okay, see the probe has come out here. And so what is this called? What is this tube called?
Ureter.
Yeah, the ureter. Okay, and then after that it goes and heads out over to the bladder. Okay? All right, so we're going to go ahead and cover that up and then head on over to the lung station. So let's go on over to the lung station. So this is a pig's lung, and you can see the alveoli in the different lobes here. It's actually really, really soft, okay? So it's like a tiny little air sacs, kind of like a mattress. So, Jessica, would you like to do the honors?
We're just inflated?
Yeah. So that's great. And so this is what's happening in your body every time you take a breath. And notice that the way that this lung is being inflated is slightly different from the way your body does it. So in your body, it's negative pressure, right? You're creating a vacuum when your diaphragm contracts. Here, the lungs are being inflated by positive pressure because we're actively pushing air into the lungs. Okay. All right, on to our next station. Okay, so for this particular station, what you want to do is take a look in your lab manual and figure out how you want to hydrate. So this is a refractometer, and what I'm doing is I'm just wiping it off really carefully and then putting some apple juice onto the surface of the refractometer, okay? And now I'm closing it up, making sure there are no bubbles, and then looking straight through the refractometer, and it looks like for apple juice, the specific gravity is about 1.07, okay? So that's actually pretty high, and I'm going to go ahead and wipe that off now and try some regular drinking water. So regular drinking water should have a specific gravity of what?
What?
What should regular drinking water have a specific gravity of?
0.0 something.
Yes, it should be basically nothing, right? And so the definition of specific gravity is 1 mil. How much does 1 mil of your solution weigh compared to 1 mil of water? So it's a ratio. So our specific gravity is 1.000, okay? And so the question is, well, what's the specific gravity of a human being? And so in your lab manual, you will see a solution that's 0.88% salt.
Sodium.
Yeah, exactly. So you should remember this from previous labs where we found out that that's the exact, that's about the amount of salt that all living cells, including humans, will have. So when you're doing this lab, or you're thinking about the data for this lab, you want to find out which drinks have a lower specific gravity and lower amount of solute than your own cells. And so just as a spoiler alert, if you were to do 0.88% sodium chloride, your specific gravity would be about 1.06. Oh, sorry, I take the back. 1.006 or 1.015. Okay. All right, so that's that. So see if you can predict, based on that information, what the specific gravity should be for a 3.5% sodium chloride solution, which is kind of like seawater. And then we also have cola, which has caffeine, and is a diuretic, if you remember, and should not be a particularly great hydration option. And then we also have an energy drink, which would be great for keeping you up, but also has, if we look in here, 27 grams of sugar. So if you just imagine how much weighing out 27 grams of sugar would be, that's how much you're ingesting when you drink 1 can of this. And it also has caffeine in it. So that, again, that's a diuretic. It will prevent the action of antidiuretic hormone from allowing your body to reabsorb water, so it will just go straight through you. Okay? All right, so what we're going to do here is test a particular patient. So I'm going to see if I can grab a little patient stick. All right, so which patient are we going to try?
The middle one.
The middle one. All right, patient B. Oh, this is. Thank you, Anita. So your peer facilitators are going to give you. Your peer facilitators are giving you a dipstick, and what you want to do for patient B is we're going to open up patient B, okay? And so we're comparing the color of patient B to the how hydrated that person is, okay? And then we're going to take our dipstick and just dip it in until we hit the very last square, and then let it develop for a while, okay? So it'll take a little bit of time to develop for a while. Okay, and then the way you read this, once it's done, is you start from the very bottom and you start moving to the top. Okay, so here glucose does not look blue, right? If it looked blue, you would know that there was nothing wrong with this particular sample. So I'm going to move it to the right until I see something that looks kind of like this color. Okay, so it looks kind of brownish, and that's 30 millimoles per liter. So that's plus plus. So that's my glucose, 30 millimoles per liter. Okay, so that's not normal, right? If you take a look at your values. Now I'm going to move up to bilirubin. That looks normal. It looks the same. Ketones look the same. Specific gravity. Okay, let's see if we can figure that out. That looks kind of greenish, so I'm going to say 1.005. This pencil is terrible. Okay, do we see the presence of blood? No blood. Let's take a look at pH. It's pretty bright, so we're going to say go with 5.0. Oops, that's in blood. 5.0. And then we don't see any presence of proteins, which is great, right? If you saw the presence of proteins, that would mean that you have some impairments in kidney function that allow proteins to get through the filtration system. And your bilinogen looks fine, no nitrites and no leukocytes. And the fact that both leukocytes and nitrites are negative suggests that there are no infections in this patient, okay? All right, so that's patient testing, urine testing for patient B. And my diagnosis for this particular patient is because glucose is so high right here, it's very likely that this patient has diabetes and should actually have a fairly high specific gravity, even though it doesn't show it here. And so one way that old-timey physicians used to test whether or not their patients had diabetes would just be to taste their patient's urine and see if it tasted sweet. If it tasted sweet, then yes, we have a positive diagnosis. Luckily, we have dipsticks now. It's great. Okay, so let's go on and take a look at the lung specimens. So this is a freeze-dried pig lung. You can see here is the trachea, right? The trachea will come down and bifurcate into bronchi, and the bronchi bifurcate into bronchioles, and those terminate in alveoli. You can also see on this particular specimen the visceral pleura, that papery stuff that's right on the outside of the lungs. Over here, we can see cross sections of this particular lung. Okay, this is a bronchus. It's not the trachea because you can see it's already touching the alveolar tissue. Within the alveolar tissue, you can see some smaller bronchi. So if they have cartilage, they're smaller bronchi. If they don't have cartilage, you can see bronchioles that go right through into the alveoli, and it's super, super soft here. Okay. All right, so moving on. Here is a diagram of, or sort of a little model of how we breathe, right? So the yellow part is our diaphragm. When you constrict your diaphragm to inhale, what happens to the volume inside your chest cavity?
Expands.
Yeah, it expands. And what happens to the pressure inside your chest cavity?
Increase pressure.
Yeah, what happens to the pressure? I'm making it bigger without adding more air. Should the pressure increase or decrease?
Decrease.
Yeah, it should decrease. And so the pressure inside your chest cavity is now lower than the pressure outside. And so what direction will air flow in? From the out to in or in to out? Yes, I'm seeing this.
Yeah.
Yeah, so from out to in, from pressure area, a gradient of high pressure to low pressure. Okay? So you can see like that. Those little green lung balloons are inflating as soon as you make the chest volume bigger. Perfect. Okay, so let's take a look and see if we can see any of the specimens. So this is a specimen of healthy lung tissue. Oh, yep, so you can see the healthy lung tissue there. It's very, very thin-walled alveoli, and the bigger, thicker red circles are bronchioles, right? So that's really nice right there. Okay, so we're going to move on to emphysema, which is right here. It's a little bit harder to see, but you can see the alveoli are a bit enlarged. I'm going to see if I can turn down the light a bit. Does that help? Okay, yeah, you can see the alveoli are kind of enlarged. They're thickened so that there's less gas exchange across all of the different walls, but you can see they're sort of blown up and exploded, so that's not great. Okay, so now we're going to take a look at a lung cancer tumor, okay, and then you can see in this particular example, let's see if we can zoom in on it. Okay, I'm going to move that around a bit. Okay, great. So you can see here we have some alveoli right there, but they're super thick and they're also completely filled in with this light pinkish cellular tissue. Okay, so because it's completely filled, there's no space for gas exchange. So that's lung cancer right there. Okay, so be aware, be familiar with those different slides. And then also think about how will each condition affect VO2 max and why? How will this affect your spirometer readings? And when will peak flow be affected, right? How does asthma affect peak flow, for instance? Okay. All right. So those are our main stations for today. We also have a spirometer where you can check out what your lung volume is, right? What your lung volume is, and all you need to do is sort of blow into it with a cardboard tube. And then we also have a peak flow meter that will actually test whether or not you have asthma, because your airways will constrict or dilate depending on how severe your asthma is. So you put on a cardboard piece here and move that to 0, and then you just take a big bolus of breath and blow, and then hopefully your the little marker will move and will tell you how quickly in liters per minute you're able to expel that air. Okay? All right, so that's what we've got for today. In our virtual lab, we will have some of these activities available for you on Tuesday if you are interested in checking out some of your own vitals and taking a look at some specimens. Okay. All right, that's all we've got, and let me know on Canvas if you have any questions at all. Otherwise, have a great Thanksgiving from all of us PFs and me.